SwayamPrabha. Digital India. Educated India.
Welcome to the class of Intelligent Product Design. So far, we have talked about design concept generation and selection of materials. So now, in the journey of our intelligent product, at least two things are there with us. The very next thing, once you have the material in your hand and your design concept is there with you, the very next thing we are going to do is to select the suitable structure for the product. Okay? That is something that we have to always keep in our mind, and I will give this particular lecture in a very qualitative manner, because otherwise the structural analysis and design itself is a full course. But I just want to give you the flavor of the essence of the design. Now, while doing it, please keep in mind that we have a famous slogan in design, that is what is called form follows the function. That means, particularly for structures, it is the function that is important and the form is accordingly chosen. Now, here there is a classic dilemma. This is one of the world's ancient terrace farming. Terrace farming today is very popular, but many of you may not know that this actually started in certain hilly regions of Southeast Asia, for example, areas in Indonesia, etc. Now, this particular case of terrace farming actually needs a decision. What is that decision? So, how much I will cut and how much I will then go, okay? Which means, in other words, these two things together is talking about a slope. So, the slope is not constant. Every time you are going, you are having a variable slope, variable angle here, and that is the decision that the experienced person can take. And the intention here is that he has to maximize this horizontal surface, so that he can do maximum cultivation without creating instability or landslide, because you know that if the slope is too sharp, then maybe there will be a landsliding, which means the agriculture will not be successful as the irrigation will be applied. So, one has to do that decision and then cut it. So, even though from a distance when I look at it, it looks beautiful to me, but more than the form, deep inside this functionality is involved here. Now, you may think, okay, this is true for agriculture, the same may not be true for beautification, but I will give you an example of it. You think of these, the eyeliners that is used, okay, for cosmetic applications. The idea here is pretty much similar. Maximize the spreading of each filament so that the eye looks beautiful. You need to maximize it without creating instability that it cannot sustain. You cannot, of course, deform something beyond a certain region, but even in order to do this, we mix some artificial material so that the hair itself does not have enough stiffness to actually sustain itself. So, we mix a material like a viscoelastic material and then we twist them, and the material stabilizes, it gives enough stiffness to the system so that you can do this. So, here also deep inside it is the form that is actually governing this whole thing, and we have to keep the selection of material keeping this form in mind. This is an example of an ornament decoration. Now, what you see here is something which is called fractals. Fractals are also examples of self-similar geometry, from a bigger scale to a smaller scale. Okay. Now, here fractals has been used to maximize the pattern complexity, because then the value of the ornamentation will increase, and this has been done without keeping in mind that you are working on the fractals on a precious material like gold or silver. So, without consuming much of the precious material, you have to develop these fractal surfaces. So that becomes a challenge in terms of the ornamentation or fashion design. Now, far from fashions, I am coming to again another product. You can understand what it is. This is nothing but a bridge. To be very specific, this bridge is one of the world famous bridge. It is called Firth of Forth, and it is a bridge which is designed in a manner that it can predominantly take the compressive load. Now, in this case also the function is to bridge this gap of the river and for maximum vehicle load, so that maximum amount of vehicle can pass without using too much of a material. That means with as minimum material investment as possible, okay, because more material means it will be more expensive. So this design, once upon a time it was made possibly by using cast iron, was an economic design, but then the structural steel has been developed, and with that the manufacturing process also has become available, so that you can give much more. We have seen in our last lecture about the shape factor, that structural steel has a much higher shape factor. So now today this type of a design is not required, because you take the advantage of the shape factor and go for other types of bridges, like say suspension bridge or things like that. So once again, the keeping the same function in mind, as the manufacturing process changes, because you should remember that tetrahedral that I have talked about, the form, material and the manufacturing, all three of them governing the function. So that is how the design keeps on changing. Again, another system, this is enclosure design. Okay. So in this case, you are covering an enclosure as cheaply as possible, because this might be for certain temporary works, greenhouse, etc., and then without sacrificing the strength, how you can do it. So that you can see here that in this design, something that has been used extensively is called truss. And what is a truss? Truss is essentially a triangulated system, okay, like this, which is designed to carry only axial load. That is the idea of a truss. So that is the way it is designed. So even if there are some forces coming here, the forces are going to get distributed only axially through the joints. The joints are all pin joints, they would not allow any moment to be carried. So that is the way the trusses, and then the trusses again are of different types, like determinate or indeterminate structures, etc., that I am not going into the details, but again this particular type of a structure has been chosen keeping this functionality in mind. Now, with all these examples, I want to summarize it just by telling that in general you will see that there are about 6 to 7 types of basic structural elements. Okay. The first one is of course tie, which we have seen in our earlier discussion. Ties are designed only for tension. Then there is strut, just the reverse of the ties, which are designed only for compression. So that means a truss is a combination of tie and strut, and together is a truss. And then we have beams. Beams are elements which are designed in a way that it can not only carry the vertical load, but also bending moment. Then the columns. Columns are predominantly for axial load, transfer of axial load. And then we have two-dimensional systems like plates, like shells. The difference between plates or shells are in terms of the thickness. If the same system is very thin, okay, so then it becomes a shell, and also shells are generally curved in nature, whereas plates are two-dimensional but like a flat panel. And in the form of shells, even thinner shells can still carry some bending moment, but membranes cannot. Membranes can only carry the sort of tensile forces, the distributed tensile forces. So these plate shells, membranes, etc., okay, or so to say the thin shell structures, you can call them to be thin shell. So, shells are thick cells and thin cells. So, all these things together, they are the basic structural element that you can consider for a particular type of a product. Now, how I am going to arrange them? That of course involves a particular team specific work. For example, this top design is using compression. So, here the theme is using compression for design, right. So, this is a pipe with spiral and radial support only, and it is designed in such a manner that all the members are having only compression. Something true here also for the ceramic ball arc. This is used as an insulator. Okay. Now, here also it is an arc like structure, and arcs, the beauty of arcs is that they can only carry compression, and that is something that is known to the mankind for a long time. Okay. In fact, one of the particular type of arches were first discovered in Indus Valley civilization, where it is not a perfect arch, but something like this. Okay. Something like this, and this is also known as, this type of a system is known as corbelled arch. So, starting from this corbelled arch, then people started thinking, instead of small by small expanding, if I lay the bricks not horizontally but vertically, then actually you are going to get a complete arch system, and the stones or the bricks are arranged vertically with the mortars. So, what is the advantage here is that this kind of a arch, particularly if it is a parabolic arch, one can show that for a parabolic arc against distributed load, whatever load is coming on the system, the forces are always compressive in nature. So, the forces are compressive inside. Okay. So, the entire system is compressive. So, compressive force. So, compression is the essence of an arch, and then taking inspiration from that, this insulator is designed in the form of a spherical arc system, which is also known as a ball arc system. So, this is where compression is used heavily. Now, there are designs where tension also is used heavily. I told you that the steel, the advent of steel has actually made different types of forms possible, the cross sections possible, and these cable stayed structures where the cables actually carry the tension. So, the tension is carried by the cable, and then these posts are getting the compressive load. So, it is the tension from the cable and compression by inside the post. So, that kind of a structure becomes very much material efficient, and it has been used for connecting bridges, for suspension bridges, or also for this type of enclosure designs like stadiums, etc. So, this is a beautiful example of a tensile structure. Some structures are neither compressive nor tensile. The best example is the space station. So, this type of structure are called balance structure. So, the space station, as you know, carrying material from the earth to the space is a great challenge, and hence it is designed in such a manner that it is completely balanced, both the tension and the compression. Again, there is another example talking about the space examples is the rocket casings, which is based on a structure which is called isogrid structure. So, isogrid, it has a sheet of material, usually metal, with kind of stiffeners integrated in it. You can see the stiffeners here integrated in it, and in such a way that they are all actually triangulation of the system. Okay. And it's exactly similar type of triangulations. So, that is something that gives a huge stiffness to the structure. So, particularly for rocket structure which is subjected to large loading, the isogrid system provides a large stiffness and strength to the system. Now, another structure also I will talk about, and that is geodesic dome, okay, which is a combination of hexagon and pentagonal structure. Now, this type of structure has a name. It is called tensegrity structure. Tensegrity. and particularly this is something that was first discovered by the famous architect called Buckminster, and later on it became world famous because a particular allotropy of carbon called carbon C60, which is fullerene structure, is also found to have the same structure. So, the name came as Buckminster fullerene structure. So, these are tensegrity structure. What is so specific about a tensegrity structure? It is a balanced system which is going to have a continuous pull and a discontinuous push. Easiest example is our kites that we use. Okay? The membrane, the paper membrane that we have in the kite is actually having these continuous pulling in it, tensile load, and the sticks that we join, one straight and one curved, they are actually giving discontinuous push. So, it becomes a kind of a tensegrity structure. So, it has been shown that given a constraint in terms of material, tensegrity structure can give you a maximally strong system if you can design this continuous pull with discontinuous pushes. Now, another important point I want to tell here is that structures, so far whatever I have discussed with you are static structures. Okay? Static structures do not have any relative motion, but there are structures which can have relative motions inside. There are structures which can be dynamic structures like a rocket, okay, like a car, like a train. So, in such structures there has to be some relative motion that happens, and then that actually moves the structure forward. Now, if you have this type of structures, then there comes three interesting elements that should be explored in terms of the design of such structures. There are three major elements I told you: the springs, the dampers or the dashpots, and the inertia elements. You think of any machine element, say shaft, say bearings, gears, belts, chains, they can all be described in terms of the springs, dampers, and inertia elements. In fact, the structures also can be discussed in the same manner. The only difference is that, suppose if I have a structure, suppose you just consider this arch to be a structure. Okay. Then if I have to design it in terms of spring, dampers, and inertia elements, we can consider that it is going to have not just 1 or 2 degrees of freedom, but countably infinite number of degrees of freedom in this system, where each of the element is joined with the other element, and in their intersections we have the degrees of freedom present, and that can be described in terms of that these degrees of freedom is constrained by either some springs or dampers or some inertia elements. Now, springs also can be of different types. Let us say linear springs, which is predominantly for the axial movement that is deformed in a way also that the force deformation, if I try to look at it, the force versus displacement, the linearity is maintained. Okay. But there can be other springs which are non-linear, like you can have a spring like this, or you can have a spring like this. This type of non-linear springs, this one is called softening springs. So, this is softening. This is of course linear, and if suddenly the stiffness increases, then this becomes a hardening spring. So, when we talk about springs, then we actually talk about all these three variations: hardening, softening, and simple linear springs. Now, springs can be used for translational movement control, or it can be used for torsional springs, like springs that is used to be in mechanical watches. Okay. So, that means which gives the resistance against twisting. The translational springs give resistance against translational movement, okay, expansion or contraction, whereas the torsional spring gives resistance against the torsional movement of the system. So, springs thus is an important part of our design, and a translational spring can be actually described in terms of two parts. the stiffness times the relative displacement. If the one end is having a displacement x1, another is x2, relative displacement of x2 minus x1 multiplied by the stiffness is going to give you the force that it is going to carry. Okay. So, many a times our design will be directed towards how to control the stiffness K of a system. Now, in a very similar manner, but slightly different expression is for the torsional spring, where it is not relative displacement, but it is relative angular displacement. So, this is theta 2 minus theta 1 is the angular displacement. Again, the torsional constant is K here, that is the spring constant, and that actually gives us the torsional force that is going to be there in the system. So, some examples of translational springs you can see that we used for many applications, and some examples of torsional springs. You can immediately think of many products where you have seen such a thing has been used. Now, many times actually they are not only used alone, but they are used together. So, there can be actually more number of springs together. And one way to determine that whether a given set of springs are in parallelly arranged or they are in series is that when they are parallelly arranged, you see there are number of degrees of freedom. Okay? And you see the number of degrees of freedom, if it equals the number of springs, then it will be series. If they are not equal, then it will be in parallel. So, accordingly, you know, if there are degrees of freedom, you can accordingly arrange the springs. Now, just like the springs, we can also have dashpots. Why do we need dashpot? Well, because if there is a relative velocity between the two ends, I may want this relative velocity to be controlled, so that it does not come like a shock load on the other adjoining systems. So, this dashpot here, what it does is that if suddenly the force, let us say, is coming at a very high rate from one side, it actually moves this entire system much slowly, so that the load is transferred, but the load is transferred at a much slower rate. So, that you know ultimately the energy gets dissipated inside the damper itself. Now, this type of damper, this is a specific type of damper, it is called viscous damper. Okay? That these viscous dampers are such dampers where the damping force is proportional to the relative velocity. Okay? So, it is proportional to relative velocity, and of course, it is linear. Okay? There can be nonlinear dampers where you may see that it is slightly different. I can try to give you an idea of it. See, it is a piston cylinder system only we are trying to draw, but this piston cylinder system is slightly different system, like there are small orifices in the damper. Okay? So, that these orifices through which the fluid can pass through from one side to the other. So, this makes the system nonlinear. Okay? So, you can have just like the spring, we have hardening, softening spring, you can have here also, and in that case you can write that the force is not proportional to the relative velocity, but it is proportional to the power of the relative velocity. So, this is also, that is why known as power damper. Okay. So, these are different type of complexities that can arise in a system. So, the figure here is showing you a linear damping system, but you can also get a nonlinear damping system, something like this or something like this, just like the spring system. So, based on the applications. Of course, I have only talked about the dashpots in terms of a viscous damping, but there are other types of dashpots also that we utilize. For example, if we have a friction that is governing the dissipation. So, this is called Coulomb damper. This is also again another nonlinear damper, and this is also used in terms of dissipation of energy. So, we have the Coulomb damper system, and then sometimes it is the structure itself where the motion of the structure actually offers the resistance. So, this is the symbol of structural damping. So, the energy dissipation is taking place because of the certain energy dissipation mechanisms inside the structure. Okay. Suppose the grains of a structure, okay, a metallic system, the grains are moving against each other and dissipating the energy, one of the examples. Okay. So, then it will be structural damping. So, you can have structural damper, you can have Coulomb damper, you can have viscous damper, that I have earlier talked about, viscous damper. So, viscous damper, which can be also of two types, as I told you, linear and nonlinear. So, we have spring as one element of a dynamic structure, damper as another important element. Finally, last but not the least is the inertia element. Inertia element is something that actually we say colloquially that it is the mass, but it is not exactly the mass, but it is something which is related to the acceleration. So, if it is related to translational acceleration, then it is related to the mass, and if it is related to rotational acceleration, then it is related to mass moment of inertia. Keep in mind here that earlier we have talked about area moment of inertia, which is required in terms of giving the sort of bending resistance or strength, or for a column resistance against buckling. Now, we are talking about the mass moment of inertia, which is important in terms of basically storing the kinetic energy of the system. Actually, each one of these systems, if we look at it, they are either energy storage element or energy dissipating element. For example, the inertia system is basically, this is a kinetic energy storage system. So, this is kinetic energy storage. Okay. Something similar to what we have done for our flywheels, analogous to that. Okay. And then the spring. So, this is about the inertia, this is about the inertia. And then when I talk about the spring, this is actually the potential energy storage system, right. So, this is potential energy storage. Okay. And then when I talk about the other one, that is the damper, this is actually used for energy dissipation. Whenever I need to dissipate the energy from the system, reduce the energy level, we need a damper. Very interestingly, I will just talk about only one little more thing to you, that each one of them has some equivalence in an electrical element also, right. So, just like the inertia is equivalent for this is a mechanical system for us, okay, and let us say I have an electrical system, then inertia will be equivalent to inductance. And if we have a spring which stores the potential energy, will be equivalent to capacitance. And if you have finally the dashpot, the third element of a dynamic structure, this is equivalent to resistance, because a resistor also dissipates the energy, whereas the capacitor and inductors stores the energy. So, thus we have the structural elements, we have broadly covered that what are the different structural elements, how they can be arranged in the form of a complete structure, tensile type, compression type, balance type, tensegrity type, and also I have talked about the dynamic structure, how they can be designed in terms of three basic elements: the spring, the inertia system, and the dashpot, okay, and how they can be arranged in series or in parallel. Thank you.